In this video, I'm going to calculate the currents flowing through each of the branches in this complex circuit. There are two batteries which will provide an electromotive force, and three bulbs which will provide resistance. Unfortunately, none of the bulbs are directly wired in series or directly in parallel with each other, so we can't use circuit simplification to solve this problem. Instead, I'll make a system of equations using Kirchhoff's loop law and Kirchhoff's junction law. The first thing to do in a problem like this is to look at it and try to determine what you think the direction of current will be in each individual branch. Then we'll draw that direction of current. Because we have a battery supplying a large positive voltage here, I'm going to guess that current is going to flow this way in this part of the circuit. And I want to give that a number. I'm going to call it I1, the current flowing through the first battery. I see there's another battery with a 12 volt potential here, and I'm just going to make the guess that the current will flow this direction through that middle branch. Now the current in the middle branch is not necessarily going to match the current in this part of the circuit here. For that reason, I'm going to call this current I2. Finally, we know that conventional current flows from a positive battery plate to the negative plate, so I'm going to guess that in this part of the circuit, current will flow clockwise, and we'll call this I3. Now, it is okay if you guess wrong when it comes to the direction of currents. What will happen is the mathematics will reveal that the guess was wrong, and I'll show later how to determine if that's the case. In this particular situation, I've actually guessed correctly. So let's go ahead now and make a couple of loop law equations for our circuit. I don't want to complicate my drawing by making my loops on top of the currents here, so I'm actually going to just redraw the circuit real quick. Alright, let's pick a point to start our loop at, and we can go either clockwise or counterclockwise, it doesn't matter. It's our choice. The direction of our loop does not necessarily have to match the direction of any particular current. The loop is all about how we're going to add up the potential changes as we move around the loop. Okay, so this can be loop 1, and I'm going to make another loop starting at this negative terminal. This can be loop 2. If I wanted, I could make a third loop going around the outside edge. I don't necessarily need to. So now we'd like to write equations for Kirchhoff's loop law. I'm going to start with loop 1. Now, as we move clockwise, we're going to go through this battery from negative terminal to positive terminal. And in that case, that means we're going to be adding 19 volts when we do that. After that, though, we're going to be going through a resistor. And I'm just going to quickly write down the resistance, 300 ohms. This one was 100 ohms. This one's 200 ohms. And so we want to show how much potential is either lost or gained in going through that resistor symbolically. But one thing to consider is our current in that resistor going in the same direction that we are going? Or is it going in the opposite direction of us? That's important. We said above that we thought current would be going clockwise in this section. So if that's the case, then when we examine the potential between the battery and the resistor, and then examine the potential after the resistor is going to be at a lower potential than it will be at this point here. Okay, why? Because current flows from high potential to low potential. So we're going to definitely lose voltage in that resistor if current truly is going that way. For that reason, I want to subtract I1 times the resistance of 300 ohms. That's going to be how much voltage we lose in that resistor. The next element that we encounter is another resistor. However, we said before that current would be flowing up in that middle branch. Now we don't know if that's the right guess or not, but according to the premise that we had set up, if current does flow up, then which point is at the higher potential? This point above the resistor, or this point below it? Well, since current flows from high potential to low, we have to assume that this is a lower potential than this point here. So we're going to gain potential as we move through that resistor. You have to imagine what it's like taking a trip all through this circuit. How does the potential change? Well, it's going to go up in this case. All right, now we're going to go through a battery, but we're moving through in a way that's not conventional. So we're going to lose potential there. According to Kirchhoffs' loop law, these four changes in potential have to equal 0. As you can see, we've developed an equation of two unknowns so far, so it alone cannot be solved. We need to use more information from the circuit in order to solve for I1 and I2. So let's use our second loop, and we'll write a new equation. So we start off here in the negative terminal of a battery. We're going to go through the normal way. So this is going to be an addition of 12 volts. And let me make it clear that this is loop 2, and this is loop 1. We're going to go through a resistor in the direction of current. So let's subtract I2 times 100. All right, our next circuit element is this 200 ohm resistor. We had guessed that I3 would be a clockwise type of current in this section. So between these 2 points, which one is at the higher potential? This one is at the higher potential, because current will flow from high potential to low potential. So we'll subtract I3 times 200 ohms And that brings us back to where we started. So that completes our loop too. We have 2 equations and 3 unknowns now. So unfortunately, we still can't solve it. The next thing to do would be to introduce either a third loop, or we could use Kirchhoffs' junction rule as well to introduce a third equation. The junction rule says that the sum of the currents coming into a junction equals the sum of the currents leaving the junction. So let's take a particular point in our circuit, such as this point, and look at the currents coming into the point, and look at the current that's leaving it. From looking at the picture, I see that the current of I1 joins the current of I2 in creating the current I3. So that's going to be our last equation. I1 plus I2 equals I3. Next, we just want to solve this using algebra. It may be helpful to just rewrite the equations without units. And there are many techniques for solving something like this. We can even use an online system of equations solver in order to get the answers quickly. If you're going to use an online calculator, you may wish to replace the variables I1, I2, and I3 with just letters such as A, B, and C, or X, Y, and Z. Now I'll plug this into symbolab.com. You just want to type each equation exactly as it appears. And we'll put semicolons between the equations. And that should do it. So I1 is A. That's 0.03 amps. I2 is B. 0.02 amps. And I3 was C, which was 0.05 amps. Now, let's just see what would have happened if we had guessed wrong. In my first attempt, I had correctly predicted that these would be the directions of the currents I1, I2, and I3. But what if I had made a wrong choice? What if I had mistakenly thought that current would flow down in the middle resistor? What would happen to alert me that this choice was wrong? Well, let me write my loop equations now. For loop 1, we would have this. For loop 2, and for our junction rule, we would have had I1 equals I2 plus I3. Because according to the currents I had drawn, I1 comes into the junction. We put that on the left, and then I3 and I2 both are leaving the junction, so they would go on the right of the equation. Now I'll use Symbolab to solve this. What changes here? According to our results, I1 is the same as it was before, but I2 comes out negative. I3 is the same. So a negative result in a current means we guessed the direction of that current incorrectly. So we'd want to go back and switch it. Now we could go back and realize that I2 was guessed to be in the wrong direction.